All right, let's jump right into complex numbers. Today, we're going to master two key techniques that show up all the time. So, if you've ever gotten a little stuck on these problems, you're in the right place. We're about to make it all make sense. Okay, so here's our focus for today. We're looking at these 5 questions. But listen, this isn't just about getting the right answers. Nah. What we're really doing is pulling back the curtain on two powerful, kind of elegant techniques that unlock every single one of these. And trust me, once you see these patterns, you'll start seeing them everywhere. So, our first technique, it's all about this super powerful relationship, the one between a complex root and its conjugate. Seriously, understanding this is a massive time saver. It's almost like a cheat code. So let me just ask you this straight up. If you've got an equation with real coefficients and you know one of the roots is complex, is the other one just a total mystery? Or is there, some kind of hidden link? Well, let's find out. We're going to start with question 5a. The job here is to prove that this particular complex number is a solution to this quadratic. Now, we're going to do this the long way first, just to really prove to ourselves that it works. Okay, let's walk through the algebra. First, as you see in step 1, we have to find z squared. It gets a little messy, but stick with it. Then in step 2, we multiply that by 5. Step 3, we find negative 2z. And now for the moment of truth. In step 4, we plug all those pieces back into the original equation. And look what happens. As we verify in step 5, the imaginary parts completely cancel each other out, and the real parts add up to a perfect 0. So yeah, the equation holds. It works. Okay, so doing it the long way proves a point, but who has time for that, right? Here's the shortcut. The complex conjugate root theorem. It's so important. It basically says that for any polynomial that has real coefficients, like the one we just saw, if you find a complex root, its conjugate has to be a root too. They are a package deal. They always come in pairs. And this right here is why that theorem is so incredible. Part B of the question asks for the other solution. So do we need to break out the big quadratic formula? Absolutely not. We just use the theorem. We take the root they gave us, we flip the sign on the imaginary part, and that's it. There's the other root. We found it in, what, like 2 seconds? So knowing this principle is awesome. But now let's put it to work. Let's try going in the other direction. What if you're giving the roots and you need to actually build the equation from scratch? Question 9 is the perfect test case for this. It gives us just one single root, 5 plus I times the square root of 3, and says, okay, find the quadratic equation. But we know the secret now, don't we? First things first, we know the second root instantly. It's the conjugate, 5 minus I root 3. Easy. Now we just use that handy formula for building an equation from its roots. We find their sum, and look, the imaginary parts cancel out, leaving us with a nice clean 10. Then we find their product, which simplifies to 28. We plug those two numbers into the formula, and bam, there's our equation, x squared minus 10x plus 28 equals 0. So cool. Let's keep the momentum going and glance at question 6. This is basically just more practice to really lock in that skill. And notice the pattern, right? In every single case, the roots are conjugates of each other. That means the sum is always a real number because the imaginary bits disappear, and the product is always a real number too. That pattern is your key to doing these super fast. All right, let's switch gears. We've totally nailed finding and using conjugate pairs. But what happens when the complex number itself is the unknown? Like it's the variable we actually need to solve for? Well, for that, we need our second big technique. And here it is. This is the master key. And it's beautifully simple. Anytime you're hunting for an unknown complex number, just replace it with z equals x plus iy. What this does is it lets you break one really complicated problem into two much simpler ones. Let's see this thing in action with question 7. We have to find the complex number z that makes this equation true. And notice, it's a little tricky because it has both z and its conjugate z bar in the same equation. So what do? We substitute z equals x plus iy. We expand everything out, and then we do the magic step. We gather up all the real parts on both sides and set them equal to each other. That gives us our first equation, x plus 4 equals 3y. Then we do the same for all the imaginary parts, which gives us y equals 3x. And just like that, we've turned a weird complex number problem into a simple pair of simultaneous equations. It's just algebra from here. And solving that little system is pretty straightforward. You find out that x is a half and y is 3 halves. All we have to do is pop them back into our z equals x plus iy form, and there's our final answer. Problem solved. Okay, let's do one more just to make sure we've got this down cold. Let's look at question 8. The setup looks a little different, but you know what? The core strategy is exactly the same. We've got an unknown complex number, this time they call it u, and we just need to find it. You know the drill by now, right? It's the same game plan. We substitute u equals x plus iy, we expand everything out, then we do the big separation. We find all the real terms and set them equal, giving us one equation. Then we find all the imaginary terms and set them equal for our second equation. We solve that new system of equations, and it gives us these really nice, clean answers. X equals 1 and y equals 2, which means our mystery complex number u is just 1 plus 2i. See? It's an incredibly reliable method. So let's just zoom out for a second and recap what we've done here. You've just added 2 incredibly powerful tools to your math toolkit for dealing with complex numbers. Technique number 1, the conjugate pair principle. This is your go-to shortcut whenever you're dealing with roots of polynomials. Just remember, complex roots always come in pairs. And technique number 2, the substitution method. This is your master key for finding an unknown complex number. Just sub in x plus iy and split the problem in 2. So there you have it. The core idea is you need to solve these problems with way more confidence and speed. But here's my final question for you. Now that you have these tools, where else do you think these things might show up? I mean, from electrical engineering to quantum physics, the world is literally built on these ideas. It's pretty amazing to think about. Thanks for watching.